To find what chord these four symmetrical elements correspond to, we can't just take 0, 1, 2, and 3 from our group and form a subgroup out of it. Keep in mind that for a subgroup to be a subgroup, or for elements to be a subgroup, the subgroup has to satisfy the same axioms as the group does. So we know that the identity element has to be in the subgroup, and each element has to have an inverse. It also has to be closed under the group operation, which in this case is addition mod 12. In the last example, it was addition mod 4. Now, don't take my word for it. Let's try as an example 0, 1, 2, and 3. If we move over 0, 1, 2, and 3, well, we have our identity element, but it's not closed under the group operation, because if we add 2 and 3 mod 12, we get 5, which is not in the subgroup. But we know that the 0, the identity element, or the perfect first, must be in the subgroup to satisfy the identity axiom. So we can take away 1, 2, and 3, and figure out what the other three elements are. Now, we also have to satisfy the inverse axiom, which tells us that each element in the group must have an inverse element, so that when the operation is applied, the result is the identity element. Since there are 3 elements remaining that we must find, one of those 3 must be its own inverse. Since if that weren't the case, one of the elements would have to have 2 inverse elements, and that's not possible. And the only other element that has its own inverse, or is its own inverse, is 6, which is the tritone. And if we look at what that means in just a moment, it becomes really interesting. But as for the other 2 elements, they obviously have to be inverse elements of each other. So we either have 4 and 5 or something else, but we also know that they have to be, again, closed under the group operation within the subgroup. So 4 and 5 won't work since 4 plus 6 is 10. 10 is not in the subgroup. So it leaves us with 3 and 9. So the 0, 3, 6, and 9 is going to be our subgroup, and this satisfies our axioms. Now when we look at what this represents, this chord is really interesting. And so this is the chord that we end up with when we look at those elements in the subgroup. It's called the incomplete dominant minor ninth, and it's the most commonly seen in dominant harmony of the diminished seventh chords. Now it's called the incomplete dominant minor ninth because the root of the chord, the A flat, is omitted, so it's incomplete. We can look at the intervals here: the perfect first on C, the minor third C to E flat, the tritone to G flat, and then the major sixth, which is the inverse element of the minor third, from C to B double flat. Now, normally, because the root of this chord is A flat, this would resolve to D flat. And so because of that dominant relationship and how common it occurs in music, we might be tempted to try to make comparisons of that chord to perhaps the identity element as the dominant or something else. But because of the abstract nature of both the mathematical field and its application, we have to realize that there's no diatonic scale in this example. The fact that we're using the interval from C to itself, the perfect first, as the identity element does not mean that is also the tonal center. Or that because this is the chord built off of the identity element, the incomplete dominant minor ninth, or that A flat is omitted, that this somehow means that there's some other relationship with other groups. This is simply a look at the symmetrical properties of these chords as well as the relationships of intervals. As far as tonal relationships, that'll come later in this course.